Okay, let's get started. I would like to welcome you all to our virtual Modeling Biocomplexity seminar on cancer invasion and progression. I hope very much that you can hear me and see the screen. My name is Andreas Deutsch. I am heading together with Lutz Brusch a group on mathematical biology with a focus on medical applications at the Center for Information Services and High Performance Computing, located at Technische Universität Dresden, Dresden University of Technology. The virtual Modeling Biocomplexity seminar team is completed by Robert Müller and Simon Sieger, who are also members of our research group. I would like to express my thanks to the director of the Center for Information Services and High Performance Computing, Wolfgang Nagel, who generously supports the idea of this new seminar series. We are quite excited. We received quite a number of interest from participants. And what you see here is not a world map of new corona cases, but it shows the registered participants. Green, here you see green and yellow are focus of attraction. And this, if you look in more detail, there's major hubs in Germany, UK, and United States, but we have also significant numbers from Spain and Italy, people showing interest in this seminar series. Just for those people far away, Dresden is somewhere in the eastern part of Europe, for those of you who don't know Dresden. And this church here is the Church of the Lady, which is a kind of landmark in Dresden. We received an enormously positive feedback when we invited for this seminar series, which is scheduled for 7 weeks, starting today until the 22nd of July. Actually, all the speakers that we invited showed enormous interest, and we are very happy today to start with Thomas Hillen. And before we start, it's a pleasure to welcome you, Thomas. It's great to have you here. It would be even nicer to have you in the same room, but the screen is okay. Thomas is actually from Germany. He studied mathematics in the University of Tübingen. He did his PhD thesis in mathematics under the supervision of Karl-Peter Hadler, who is one of the pioneers in biomathematics, one can say. And the PhD thesis was on nonlinear hyperbolic systems in context of Turing patterns. Thomas also did his habilitation on transport equations in Tübingen and then left for Canada and starting as assistant professor, now today full professor in University of Alberta. He is actually having many rich experiences in teaching, and I would like to recommend his book, Course in Mathematical Biology. Thomas is not only member of prestigious scientific societies. Today he is the president of the Canadian Applied and Industrial Mathematical Society. His research interests are multifold. There is a focus on definitely biological transport. And I would like to recommend his key reference, A User's Guide to PDE Models for Chemotaxis. And in the last years, Thomas has increasingly taken interest in cancer. And today he will speak about his immune-mediated theory of metastasis. Before, Thomas, you get the word, some technical comments. There is a chat function in YouTube. So if you should exceed the capacity limit in Zoom, you can switch to the YouTube channel and use the chat function. In Zoom, please use the Q&A function. We will collect all the chat questions and later use them as a basis for the discussion. That's the plan. And now we are looking forward to your presentation, Thomas. Thanks for being here.
Yeah, thank you too, Andreas. Yeah. So we should probably switch the screen, right?
Yes.
Okay. Yeah, before I share my screen, so thank you, Andreas, and your team for the invitation to talk here. I know this is new for everybody. So for me, it's the first online talk, I think. For you guys, it's probably the first one in the series. So we have a few technical glitches to sort out. So let's share my screen here. Yeah, so that should do it, right? You all see Adam in front of the balloons. So this is joint work with Adam Rhodes on cancer metastasis. Honestly, I find in this time of coronavirus, I find it very hard to think about cancer because everybody is thinking about coronavirus and how it spreads and how it infects. And people are discussing what it does in the body and how it interacts with the immune system and all this kind of stuff. And a new thing there is that we actually understand what's going on, right? So many of us are mathematical modelers in biology, and we know what models are, we know what models do and what they cannot do. And so it's rather straightforward for us to follow the discussion. And of course, then you also get involved and you get kind of absorbed into all this discussion of coronavirus. However, cancer continues too. Cancer is a very devastating disease, and we should not stop and we should not falter our efforts in researching cancer as well. So this is a talk about metastasis. And so yeah, 90% of cancer deaths are related to metastasis. So that's why many people think metastasis is a very late occurrence in cancer. But this is not necessarily true. As Hanin, for example, showed, metastasis can arise rather early in the disease. Okay, talking about metastasis, you get already into trouble. So if I talk to a clinician or a biologist, then they will ask immediately, what kind of metastasis are you looking at? Looking at breast cancer, which maybe metastasizes to the brain, or prostate cancer, which goes to the bone, or melanoma, which metastasizes in the skin, etc. And so the question is, what as a mathematician can you actually do on a more general level or a more systematic level? Is it really okay to talk about like a default metastasis or like a typical metastasis? Does this really exist? Yeah, I don't know. But we will see in my talk if it's really possible to make some useful or to gain some useful insight through this kind of analysis. So let me start with the metastatic cascade, just what the common understanding is. So I wanted to draw a tumor, but tumor should not be red. The blood vessel should be red. So here, let's say, is a primary tumor. And let's give it some blood supply. So maybe here's a blood vessel, which is connecting to the cancer, or maybe not. Either way. Okay. And then maybe this might be connecting to another organ, let's say the liver or something. So then typically the metastatic process is divided into 5 steps. The first step would be a form of local spread, so that metastases or cancer cells manage to loosen from the primary tumor and then invade the local area until they find a blood vessel. This is also related to the EMT, epithelial mesenchymal transition. And then they enter the bloodstream, which is called intravasation. And of course, then they're transported by the blood The blood is in general relatively hostile to the cancer cells, so most of them will perish, but not all of them. So some make it through the blood system, and then they can either get stuck in very small capillaries, or they might even be actively attracted, some form of chemotaxis, into a distant organ. So there's extravasation. And then if the conditions are favorable, then they might form a metastasis right there. Okay. So far so good. So this process is relatively well understood. And people look at all the details. There are groups looking at intravasation dynamics, people looking at extravasation dynamics, etc. However, there are some very curious occurrences in metastasis. For example, one is, why do metastases often go to the bone, to the lung, and to the liver? So there are certain patterns. For example, prostate cancer shows this pattern. They go to the bone, lung, and liver. And there are other cancers which go to other organs. And I think it is not very clear why this is the case. There's a certain map or a good understanding where typical metastases show up, but why is not very well understood. Another interesting question is dormancy. So it is known that metastases can lie dormant for a very long time. Even after the primary tumor has been removed, they still might exist and be dormant for years and years, and only after a certain time then they come and start and form a metastatic tumor. Another question is metastatic blow-up. So what's also observed quite often is that after surgery, all of a sudden metastatic blows up. A metastatic cancer arises very quickly and becomes very, very large. So this is called metastatic blow-up. And it must have to do with the removal of the primary. There must be some form of interaction between those two. Another curious occurrence is metastasis to sites of injuries. For example, it has been reported a few times that cancer patients who have dental surgery, that they then get metastasis right there where the dental surgery was, at the bone of the mouth. There are other reports where people have injuries and then they form cancer there. There is the famous case of Terry Fox. Terry Fox is a very famous cancer case from the 70s, I think, in Canada. He was diagnosed with cancer in the leg, and he got a part of his leg amputated. But then he tried to run through Canada with the amputated leg. And so that's a very interesting story. Now, in his case, it is discussed if this could have been due to metastasis to injuries. Because earlier he had a car accident and he broke his leg. And then this was fixed, but he was also a runner. He wouldn't wait. He wanted to run early. So there was the inflammation in the leg. And he had already lung cancer at that point. So maybe the metastasis went right there, where he later developed bone cancer in the leg. Okay. Metastasis related to chronic inflammation. There's a large research area which looks at obesity and cancer, and obesity is related to chronic inflammation of the adipose tissue. And this is also not a good prognosis for cancer patients. And then finally, metastases sometimes do not react to immunotherapies. I'm sure you all have heard about immunotherapies. It is, many people have lots of hope on this kind of therapy, but it's also shown that in metastasis, it sometimes does not work, or in very few cases, it has even made things worse. Okay, so these are all effects of metastasis or observations on metastasis growth, which cannot be explained by the metastatic cascade, which I've shown earlier. But in this cascade picture, you would have a primary which kind of feeds a secondary, and then the secondary can grow more or less independent of the primary. And this doesn't seem to be the full story. So there must be something else going on. And this is what I'm after. Now, if we look at these items here, in particular the last three, they all have to do with inflammation. So they all have to do with the immune system. So injuries is an area of increased immune response. Inflammations, immunotherapies, you even insert active immune cells into the system. So it looks like that the immune system plays an important role in the progression of metastases. And maybe it is not only controlling the tumor, it might actually be supporting the cancer, supporting the tumor. But if it has to do with injuries, you have lots of immune cells. And then if a cancer arises there, maybe they like to be around immune cells, which would be a very strange thing to do. So the candidate here in our modeling is the immune system. So what is the role of the immune system in the metastatic process? And can this explain all these kind of curiosities which are listed here? So this idea for me started with meeting Laili Shahriari. She is now assistant professor at the University of Texas. She was a postdoc at the MBI in Ohio when I met her in 2015. And we had a nice talk about cancer and modeling and so on. And she talked about the idea that actually the inflammatory process is responsible for metastasis, or at least helps metastasis to form. She wrote a wonderful article in F1000 Research. A new hypothesis: some metastases are the result of inflammatory processes by adapted cells. So there are two ideas here. The one is that the inflammation helps the cancer, but the other is the word adapted, the adapted cells, so that the immune cells are changed through the interaction with the cancer and become tumor promoting. So that she read a lot of literature, and I'll show you a bit more literature in a second. And she came up with this idea that there's some, you could call it education, so that the tumor educates the cancer cells. The tumor educates the immune cells to its own favor. So let's look at the literature. So there's more evidence to that. Here's an old paper of 2005 in Nature, where you can see in these images that you have bone marrow derived cells invading first. So these are immune cells, and these are the green cells in these images. They come first to a certain part of the tissue, and then the cancer cells come later. So this is also seen in this graph here. So the green ones is the immune cells, and then the red ones are the cancer cells. And also it's spatially correlated. So wherever there's a lot of green cells, this is then also where you see red cells after a while. So it seems like that the immune system prepare a niche. They prepare the space for the cancer cells to invade to. Right. Here's another paper, 2015, inflammation-mediated metastasis. So this relates to the endoepithelial to mesenchymal transition, where then cancer cells become active movers and active invaders into the surrounding. And then there are a few more papers. Maybe I'm not listening them too long here. I rather would like to explain the effect on a few graphs. Yeah, so this one. So here, let me explain, for example, macrophages, how macrophages will work. If there's an injury in the body or a cancer, then the first to arise will be M1 macrophages. And these are the good guys. These are the guys who eat infected cells, if you talk about a virus infection, but then they also destroy cancer cells. And I would expect that most cancers actually already die at this level, and you will never see about them, or you never feel them, because they're controlled by the immune system. But if the tumor becomes too big, after a while, then the M2 macrophages show up, and the M2 macrophages are responsible for wound healing. So they try to close a wound, to produce new tissue, to produce new blood vessels, etc., etc. So they release growth signals, but then these growth signals can be also seen by the cancer cells, and they happily eat them, and they grow as well. Another class is the tumor-associated macrophages. I'm not quite clear if they are the same as the M2 or not. Maybe one of the listeners knows this. I think so far they're only classified by the action of what they do. So tumor-associated macrophages induce angiogenesis. They induce motility of the cancer cells, and they also help in the metastatic formation. So here you have one specific effect already where macrophages can be either way. They can be anti-tumor or pro-tumor. Here's another a relation of T lymphocytes. So T lymphocytes are part of the adaptive immune system. They would come in later in a wound healing process. And they are the CD8 plus T cells, which fight the infection or which would fight the cancer. And then the regulatory T cells, they would protect. And if the cancer now manages to convince the body that the cancer is actually a new organ which needs to be protected, then the regulatory T cells come in and try to shut down the immune response. And in this way, they are also helping, of course, the tumor to grow. Yeah, I think here I have one more example of fibroblasts, which in particular for lung cancer have been shown to be cancer promoting angiogenesis, promoting invasion, and even promoting drug resistance. So now drug resistance is something I will not talk about in this talk much more. So it looks like the immune system has this face. It is like a good cop, bad cop situation. So on the left, you have the good cop, the good immune system, which tries to control infections, inflammations, injuries. But on the right, they can be maybe turned and then become promoting for the cancer and no longer helping the body. So that's the working hypothesis about this. All right. So the transitions here, M1, M2, and tumor-associated macrophages is continuous. So it's a gradual increase. They're not just like 3 classes of macrophages. They can have several characteristics. Same for fibroblast and cancer-associated fibroblast. These transitions are gradual. John Kim just showed me rather recently the relation of neutrophils, and they call them tumor-associated neutrophils, which are upregulated to TGF-beta and downregulated to interferon beta as well. So lots of evidence for this effect. Okay. Yeah, so I want to slowly come, of course, to a mathematical modeling of this process. And before I do this, let me discuss a few models which have been done so far, in particular for metastasis. And there's a whole branch of work on stochastic models, which I think makes a lot of sense because forming of metastasis is stochastic. You don't know where they arise and you don't know if they arise. And the first and foremost, the first idea should be to use a stochastic process. And I think this started with Liotta in 1977. And then Franziska Miescher has done a lot of work on this. And then Hanin, that's the guy I mentioned already. He looked at the natural history of metastasis and he showed that metastasis can be rather can arise rather early in the progression. Together with Adam again and Chris Fry, a colleague, we looked at a branching stochastic process with settlement. So where we use these stochastic ideas in a spatial context and try to help to answer where do metastases spread and how often do they spread, and maybe even derive something like a metastatic reproduction number. Okay. There are PDE models. Since I'm talking about the spatial context, the spatial context is important. So Iwata has an important PDE model, which then has been used by Benzakri and his collaborators to fit it also to clinical data. And in this context, yeah, I have worked on birth jump processes, which are also PDE models. And then here in this block, these are now models which include the immune system. There's a basic model by Kuznetsov, and all following models basically use the ideas from Kuznetsov. For example, there's Enderling's paper here. I know Heiko is on the call, so I certainly should mention him. So about dormancy, blow-up, abscopal effects. So in particular, you see dormancy, blow-up. These were 2 words which I mentioned already in my introduction as curiosities for metastasis. And so in Heiko's model, these effects can be explained. Now, these red highlighted references, these are the ones which then also use a pro-tumor effect of the immune system. So this has not been included in the other models so far. In particular, starting with Avner Friedman, he looked at the macrophages M1, M2. Wilkie Hanfeld, they looked at concomitant resistancy experiments. So these are experiments where you have a mouse, say, and you insert two cancer tumors into the mouse at different locations. And then you see if they grow in parallel or if one grows bigger and the other grows smaller, etc. So, so that kind of work. Okay. And then lastly, and this is what I'm going to talk about now, will be the immune-mediated theory of metastasis, which I worked with Adam. Okay. So let's look at the effect of metastatic blow-up. So that's the effect that the primary tumor is removed, and then all of a sudden the metastatic tumor grows, and grows very quickly. And there are four theories which have been brought forward, which could explain or could help to explain this process. Theory one is a resource monopolization. So maybe the primary tumor has some resources available and it uses all of them, so nothing else is available for the metastatic cancer. But then if you take out the primary eater, the primary resource, then all of a sudden you have resource for the metastasis. So if I don't know, if you have two cats at home, a bigger cat and a smaller cat, then you know the problem that the bigger cat would eat all the food until it's satisfied, and then only the smaller cat has time to eat. And of course, people have all kinds of strategies to put them in different rooms, etc. So that's the theory number one. Theory number two is an immune surveillance, so that the immune system tries to inhibit both primary and secondary. And because the secondary is smaller, it has a better chance to control it. Theory number three, local promotion, global inhibition. People were looking for cytokines, chemokines, which are signaling molecules, and then they signal the secondary cancer to become small or not to grow that much. And then the fourth one is the one I'm going to talk about, which is the role of the immune system in both antagonizing to the cancer and promoting to the cancer as well. So now let's look at the effects I'm after, like dormancy, blow up, metastasis to injuries, metastasis to chronic inflammation and immunotherapies. And then I made a few check marks to show which theory can explain which kind of effect. And you see, as soon as you include the immune system, like in injuries or inflammations, you probably cannot ignore the positive effect of the immune system on the metastatic process. Okay. And of course, I'm going to show you evidence now in a second. So now let's come to the model. Here's again the metastatic cascade. So we have a primary tumor here. Okay, yeah, it's hard to see my pen on this. They intravasate into the blood system. They're transported through the blood. They extravasate somewhere here, and then they form a metastasis there. But now I would like to include the immune response as well. And I have two types of immune cells. I have the cytotoxic immune cells, which, can you hear my phone ringing? This is annoying. I'm sorry. Okay. We have the cytotoxic immune cells. They're indicated by the symbol here, and they kill cancer. But then we assume they can be educated, and we use this little doctoral hat symbol for the educated immune cells. And then they help the cancer, which is indicated by the cup of milk. So they produce growth factors, and by the shield. So they also shield again for the immune attack. And now these immune-educated immune cells, they can also be transported through the blood system. They can also extravasate, and they can also populate the metastatic area. And so then this way helping the metastasis to grow. Okay, so the analysis of all this will be in 3 stages. Maybe I show them all at one page. So the full model will have 8 ODEs, and I'll show this just quickly in a second. It's a detailed model for the immune dynamics, for the cancer dynamics, for the recruitment, and for the immune education. And this model can be used to study dormancy, blow-up, injuries, immune therapies, everything. But then it's also limited in what you can do. This model has 70 parameters. We know about 40 of them. So for the other 30, we had to make educated guesses. And so this is not very satisfying, of course. So then we reduce the model to 3 ODEs by just focusing on the metastatic side. And there's much more we can do. In particular, we can also do some mathematics. So we can do a bifurcation analysis, for example. And we did do some parameter fitting here for data from breast cancer. And then it turned out for the 3 ODE model, we can do further reduction using singular perturbation ideas, and to come away with the 1 ODE description of this process. And this sounds rather crazy. So if I would have told you at the beginning that I tried to describe the metastatic process and the immune system and everything with 1 ODE, you would have called me crazy. But math is fun. So using advanced math, we can actually reduce it down to a 1 ODE situation. Okay, and of course, this is what I want to show next. So let's start with the 8 ODE model. So we have 2 sites, IS1 and 2, primary and secondary tumor sites. And then we have the tumor cells U, necrotic cells V, cytotoxic immune cells, which we call CT immune, which is X, and tumor-educated or pro-tumor immune cells, TE. Right, and the idea is that we have some education, so we can go from X to Y. So the tumor can kind of educate or change the phenotype of the immune cells in its favor. All right. Yeah, so then here is the model. Of course, many of us have seen these kind of slides many, many times over. It's very basic modeling. We look at the interactions. You do Michaelis-Menten kind of reactions whenever you can. There are a few saturation functions going on. So maybe I want to just mention a few. Which one do I want to mention? Oh, the growth stimulation through Y. So let's look at this term here, gamma of Y. Okay, so Y1 are the educated immune cells, so they're helping the cancer. And this is the growth term for the cancer. So this is now modified by this dependence on Y. And this gamma of Y would then be an increasing function, something with a saturation, so maybe something like this. So if the tumor-educated immune cells are 0, then there would be no change in the growth law. But then they can promote the growth, and we just let it go to 1.5. So it's not so drastic, but there's a positive effect of the tumor-educated immune cells. And then similar here, in the death term of the cancer, there's also a Y dependence, which is then decreasing. So if you have more tumor-educated immune cells, then the death rate for the cancer goes down. So it's a protective effect. Maybe that's enough what I should mention on all the detailed functions here. Okay, so yeah, I said this, we have about 70 parameters, and we have to make choices for several of them. So let's look qualitatively what the model does. And here I want to show the 3 steady states which arise. So this is a disease-free steady state. So the black curve here, this is the tumor. And you see it goes down very, very quickly. And also on the secondary side here is a tumor. It goes down very, very quickly and then approaches a 0 steady state. So patient is healed. We can send him or her home and we are done. And so this is good. You also see the cytotoxic immune cells. These are the blue line here. They reach some homeostasis level. So they're basically controlling the environment and keeping everything clean. Okay. There's another steady state, which is metastasis only. So here again, you see the black line a little bit. The tumor cell goes down very quickly, but then the metastasis, they can actually grow after a much later time. So in this simulation, it's maybe a year later, you all of a sudden get metastasis forming. And this is also a steady state of the system. So it is possible that there's only a secondary tumor. And then of course, you can have a full disease where then you have a primary cancer and a secondary cancer as a steady state of the system. Okay, so far so good, this makes sense. Now let's come to the results, what we can do with the model. So the first one would be to look back at the data from Kaplan from 2005, where you have the bone marrow-derived cells come first and the cancer cells come later. And then in our model, you can have a similar effect that the immune cells come first, and only after the immune cells have settled, the cancer cells show up as well. So here's now like a numerical experiment for primary resection. So what you see is that here the black line would be the control. So you just let the secondary tumor grow and do absolutely nothing. And then you take out the primary tumor at different points in time, and you get different results. So in the green curves, you took out the primary tumor early enough so that then the metastasis actually goes down. These are all the green curves. In the red curves, you waited just a little bit longer before you're taking out the primary tumor, and then you got an increase. You got a very quickly increase in the metastatic growth. I should say, to clarify, this is still not called Blowup because to control the black line, right, this would be the growth of the metastasis without any intervention. And so without any intervention, it would be worse. If you do a primary section, then the red curves still grow, but they grow much later. So there's certainly something to be gained. Okay. Here's now a study where we compare this to the action of the immune system. So again, the black line is the control. But now we include a phase here, this little pink band, where inflammation is increased. So by taking out the primary tumor, you produce an injury, and then the injury, of course, activates the immune response. So there's a certain window, and we assumed it's about 1 week, where the immune system is increased. And let's see what this does. So then this is a situation here, the red one. If we just have the normal immune response in our model, then you get a long period of dormancy of the metastasis, which is the blue bar there, after it still grows. If you reduce the immune response, which is a pink line, then you still get the dormancy, but eventually the metastasis actually decays. And in this model, if you have no immune response, which is a green curve, then you get a quickly actually decay of the metastasis. So it's very counterintuitive to what you would expect. So if the primary resection gives no boost to the immune system, then in this case, the metastasis would actually disappear. And then we also looked at the education rate. The education rate is the rate where the X are transformed into Y, so the cytotoxic immune cells to the educated immune cells. If the education is reduced, then also you get a more positive effect, and the metastases disappear. Now here's a little simulation for immunotherapies, where in immunotherapies, the idea is you just boost the immune system, you take immune cells out of the body, you replicate them externally, you put them back in, and then hope they fight the cancer. And what we show here in this reversing arrow is the invasion speed, number of cells as a function of time at the secondary site, depending on the amount of cells you boost, the amount of immune cells which you add. And then you see if the amount of immune cells is too large, then you can actually increase the time, or actually increase the growth of the cells, reduce the time it takes for the cells to grow. Here's an example for injury. So on the left, we have a situation where the primary tumor grows to something like a carrying capacity. On the right, we have a secondary site where we introduce an injury at time, right here, at time 140 or something. And we simulate the injury by boosting just the immune response. Actually, no, boosting the dead cells, right? And then the dead cells triggers an immune response, and then the immune response prepares a niche for the cancer. And then after a while, we do see metastasis forming right there. Okay. And I jump that one. Yeah, so it seems like, I mean, there are like 70 parameters. You can probably model everything. How do you say, you can model an elephant who wiggles with his trunk or something. And so it's a big model, and it's no surprise that you can have all these effects. So let's look at the reduced model. And here we assume the primary has a steady state. And we just use a primary now as a source term, which is feeding the secondary site. And it's feeding not only cancer cells, it is also feeding immune cells into the secondary site. So then the model for the secondary site has only 3 equations: tumor cells, cytotoxic immune cells, and tumor-educated immune cells. And then that's here. Now, 3 equations, of course, is much easier to handle than 8 equations. And so let's do some math with this. In particular, a multiscale analysis, because the tumor dynamics is slow, right? So the cancer grows over months and years. The immune response is quick, in particular in this context. So immune response is in the order of hours or days, and the tumor grows in the order of months and years. So we can introduce a little epsilon for the immune cell dynamics, and then use our framework of singular perturbation or perturbation analysis. So let's do that. And then for small epsilon, using geometric singular perturbation theory, we can show that the dynamics lives on a slow manifold, and the slow manifold is given here by this formula. The slow manifold is the manifold where these 2 functions, G1 and G2, are 0, and G1, G2 are the right-hand sides of the equations for the immune response. And on this manifold, we can indeed reduce the dynamics to 1 equation. U dot is f of u and x and y. And that's really cool. So let me show you how this works here. So here, first of all, it's a slow manifold. So you have the manifold where G1 is 0, you have a manifold where G2 is 0, and where the 2 intersect, which we try to show here. And then this is the slow manifold, or we taken it out here. This is the slow manifold where the system lives on. We compare this to a numerical solution, which is a black line here. And the numerical solution, as you see, is very, very close to this slow manifold. Okay. And so then here is what happens on the slow manifold. So I just remove the upper one. I just want to show these 2. So now on the slow manifold, you have just a function f of u. Okay, so here's the u-axis. And for a certain set of parameters, you get this like wiggly function, which has a few zeros, and these are steady states, right? And so then this one would be stable. This one, the open circles are unstable, stable, unstable, and this one is stable. So you can really use your most trivial 1D phase plane analysis for this kind of model. So it's really cool. And then down here, we show the solutions and how they then converge to the different steady states. So what can we do with this? Let's see. We can come back to the primary resection experiments now for the highly reduced model, and we can better understand the effect, what's going on. So here on the left again, we have the control case in black, and then we do a primary resection, and we get 2 types of curves, the red ones and the green ones. The green ones correspond to an early resection where we have success, and the red ones is the late resection where we have no success. Now looking at the slow manifolds here, we have two slow manifolds. One is before the resection and one is after. And now I need just to make sure I identify them right then. So the upper one is before resection of primary, and then this one here is after. So the system changes, the slow manifold changes, and then the trajectories which were earlier on the red curve, they now fall down to the green curve, or blue. It's blue. Here you can see it's blue. Okay. So they leave the black curve and they fall down onto the blue curve. And then here is a saddle point. And now it depends on which side of the saddle point you land. If you land on the left of the saddle point, you get a growing tumor. If you land on the right of the saddle point, you go down to 0. And these are the red and the green curves. So it gives you a very good understanding of the dynamics, how it works. And down here you see the corresponding phase planes on the corresponding slow manifolds. And again, here's the saddle point right there. And you go either left or right, depending on which side you land. So let's come back to the blow-up. Now for the blow-up, I earlier mentioned we had like 4 theories which can help to explain it. And so here we look at 4 cases. Case 1, we have 100% removal, primary removal, but no inflammation. In case 2, we have 100% removal and inflammation, which is induced through the removal. In case 3, we have both of this and an increase in education of the tumor cells. And then in case 4, we look at a small percentage of removal. I talk about this in a second. But for the first case, 1, 2, 3, we see that case 2 and 3 can explain dormancy, and case 3 can explain dormancy and blow up as well. So it seems like we tried many things, but it seems like an increase in the education rate or some increase in the education efficacy needs to happen so that blow up can be explained in the model. Okay, the small percentage, here I'm thinking about biopsies. Biopsies is if there's a tumor and then the clinician takes out just a small probe of tissue, this still induces an injury and it induces an inflammation there. And maybe even this can trigger tumor growth or can trigger metastatic growth. And so this is a situation we studied as well. Okay. So yeah, oh yeah, here's the biopsy thing. So there is a little bit of indication. So preventing inflammation inhibits biopsy-mediated changes in tumor cell behavior. So this talks about if you do a biopsy, you should also reduce the immune response so that is much safer for the patients. And here's another one. Acute inflammation induced by the biopsy of mouse memory tumors promotes the development of metastasis. So these papers indicate that actually biopsies could help in the metastatic process, which is very crazy because biopsies are usually considered to be safe. So here is a report by the Mayo Cancer Clinic where they very clearly say that biopsies are good. There might be a little risk, but there's so much which you can learn from a biopsy, and the treatment can be then really designed for each given patient individually based on a biopsy. So the positive effect of biopsy certainly much outweighs eventual risks that can happen. Okay, but now how does this work within our model? How does this look like if we use our model for this situation? And this is here. So now we took our model and we introduced a small injury at the site of the metastasis as a secondary site, just to see if a biopsy could trigger the growth. And then here on the left, you see a diagram which depends on the influx rate phi and the inflammation level on the other side. Okay, and then this little blue wedge here, this is an area where the biopsy can actually entice cancer to grow. Okay, so which means it is mathematically possible, but it is also very, very unlikely. It is only a very small and very specific case, which is very unlikely to happen. Okay. Yeah, I think then this is the last result, and then I'm about to finish. So here we look at again at the cases where the resection leads to success or failure. Unfortunately, we flip the colors. So now the red ones are the good ones where the cancer disappears, and the green ones are those where the cancer keeps growing. And we take out this bit and enlarge it here. And then you can distinguish the green and the red curves already in this time interval, which is about 3 weeks. So by following the immune dynamics in a period of 3 weeks after resection, you can already make a prediction for the long time, for the long time behavior of the metastasis. So this could be a useful diagnostic tool. Instead of waiting too long, you can follow the immune response for the next 3 weeks, and then this might help you to understand how the long-term progression is. All right. Yeah. So let me conclude. So we have the good cop, bad cop situation. The pro-tumor effects of the immune system are well established, and more evidence is gained every day. The exact process how tumor influence the immune cells and change their phenotype is unknown. So what I called education, it is not very well understood how this actually really works. However, the inclusion of this tumor education can explain all these processes which I have explained earlier. I didn't talk about 5 bone, lung, and liver, but it should now be obvious because these are tissues where there's lots of immune activity. There are lots of immune cells hanging out, in particular in the bone. So based on this theory, you would expect lots of metastasis in the bone. Okay. I think now, coming back to my initial question, that these kind of insights would not have been possible without mathematical modeling. I think this is really a role math can play to see things from a more general level or more abstract level, but then also to find relations and I want to say find relations and structures which are maybe invisible if you only look at one particular cancer, let's say breast, and only at one particular metastatic site, let's say a brain. Okay. Of course, if you use this for the patients, patients are all different and cancers are all different. So this is not a one-fits-all approach. So if you really work with patient data, you need to do much more of the model fitting. Yeah, and so, but what this tells me also, it might not be enough to look at the genetics of the cancer of a patient. You might also want to know the genetics of the immune system to have good information about possible treatment ways. So this is, of course, future research. All right. So yeah, so that's the end of my talk. Let me thank again Adam, who has done much of the work, a wonderful PhD student. And here are the 2 publications we're working on. And thank you very much.
Yes. I'm clapping and in expressing my thanks and probably of all the participants for your wonderful talk, connecting highly relevant medical applications to mathematics. And we have already received some questions in the chats, which I like now to share with you, Thomas, and with the seminar participants. You are still invited to add questions in the chat of YouTube and in the questions and answers function in the Zoom. So let's start with a question by J. Jen. Would it be reasonable to assume at least some immune cells could also, instead of paving the way, just lose the battle against the metastatic tumor cells? In one of the earlier articles, I saw the number of immune cells also being diminished after the rise of tumor cells. Couldn't this also explain the effect of dormancy? Thomas?
So both answers are yes. So first of all, we have this in the model as well, that the immune cells perish from the interaction with the cancer. So this is already included, and this effect can also explain dormancy. That's right. I think this would be, for example, in Enderling's paper, who has done that as well.
Mm. Thank you. And now a question by Heiko Enderling, who you just mentioned. He's very specific. On slide 36 or 37, the full ODE model, could you please comment on the motivation to include necrotic cells in the model? They only seem to contribute to CT cell recruitment in addition to non-necrotic cancer cells.
So let me show this once again. Andreas, maybe remind me of the question once more.
So the question was referring to the full ODE model, which you have here.
Mm-hmm.
Could you please comment on the motivation to include necrotic cells in the model? They only seem to contribute to CT cell recruitment in addition to non-necrotic cells.
Yeah, so right, you gave the answer already. So the main reason is that we use the necrotic cells to stimulate the immune response. Yeah, that's the main reason we do it.
Okay, thank you. We have a question from Mexico by Josue Nava. If I understand correctly, does the model assume that metastatic cells are randomly disseminated throughout the body and can only thrive in sites with an already high number of cytotoxic cells?
This is a very good conclusion of this, indeed. So what this model basically implied is that the immune system can prepare a niche somewhere in the body, and then the cancer cells, when they come by, then they like it, and then they stay. Mm-hmm. So yeah, I think you're right.
Another question by Heiko Enderling. The model so far seems to simulate a single metastatic site that may be promoted by removal of the primary tumor. Do you expect the results to be different if there were multiple metastatic deposits?
Very good question, Heiko. Thank you very much. I currently have a student who is working on this. And of course, if you have different metastatic sites, they also have different parameters. So then the idea is to look at sites in the liver, in the lung, in the kidney, and so on. Have different parameters for those. Let them communicate with each other and then see what happens. Yeah, so this is now ongoing work, and I don't know what's going to come out. Yeah.
Here's another one, Thomas. Is there some non-invasive way to measure the bad cop immune response, which means some kind of marker within the blood?
I think this would be just super fantastic. So it is possible for the macrophages, so you can distinguish M1 and M2 macrophages by their gene expression. I don't know how good this is possible for other immune cells, but you're right. In particular, with immunotherapy, when you take out immune cells from the body, it might be very useful if you can distinguish them into two classes: tumor promoting and tumor antagonizing.
And here we have a question from Scotland, from University of Dundee by Dumitro Troko. Hi, Dumitro.
Hi, Dumitro.
His question is, could space be considered in this modeling approach? Thomas.
Yes, of course. I mean, space can always be considered. Right. So here we really wanted to focus on the role of the immune response, and that's why we didn't use space. But yeah, but other modeling approaches use space as well. I don't see much sense in throwing a diffusion term in all the equations. I don't think this is very useful. I think the questions to use a spatial model should be different, or they are different. Mm-hmm. Yeah.
So here's the question by Raktim K. what is the relation of metastatic cells and immune cells in the cancer model?
The relation of the metastatic cells and the immune cells.
In the cancer model.
Yeah, okay. So there are two relations. One is the cytotoxic immune cells, they kill the cancer cells. The other relation is that the cancer cells can educate the cytotoxic immune cells to become tumor-promoting immune cells. And so they change their phenotype, and then they help the cancer to grow.
So while we collect further questions, I have a little question to the magic of your talk. Here we see this full system of 8 equations, and you reduce it to 1 equation.
Yeah.
Can you maybe very shortly explain again how the whole dynamics is encapsulated in this 1 equation? I know
yeah,
magicians usually don't share their tricks, but please make a little exception for us.
The key is the different timescales. What I said somewhere during my talk, that the immune response is relatively fast and the cancer progression is very, very slow. And this gives you basically the key for this model reduction. So they can always assume that the immune response is in quasi-equilibrium, and then simplify the equations that way. So that's it in a nutshell. Yeah.
And now we have the second question from Dresden or Berlin. Simon Züger is asking, does your model predict that taking immunosuppressants may be a good idea in some circumstances?
Yes, and it is done in some circumstances. So it is in some clinical trials, they try to combine a treatment with an immunosuppressant, like radiation treatment, with an immunosuppressant to actually reduce the immune response in this case. So this is certainly done, yeah.
And another question by Xi Yang. Have you considered other mathematical tools such as game theory?
Now, this is easy to answer, so I have not.
Do you think it's worth doing it?
It's
What
absolutely
additional?
worth, no, it's absolutely worth doing it, yeah. This might actually show up at the very last talk in your series, right in the talk of Bob Gartenby, where you said evolutionary ideas for cancer metastasis. And I think he's using ideas from game theory, but of course, I'm not giving his talk, so we have to wait maybe another few weeks.
Okay. You need a glass of water, Thomas, or are you ready to answer a further question?
Sure.
Okay. So the next question is by Fanush Farapur. Do you think that these educated immune cells could be mistaken in immune repertoire data analysis with expanded colons responsible for the immune response?
I think they could. This relates back to an earlier question, if you can distinguish them or not on their genetic makeup, and you cannot in all cases. It is not very clear what the genotype is or phenotype is of these tumor-promoting immune cells. So I think they can be easily mistaken the wrong way. Yeah.
So what is, we have the innate and the educated immune system, and in your equation system, both play a role as far as I understand, no?
Well, so the example of the macrophages, this would be the innate immune response. The T cells, which I mentioned, would be the adaptive immune response. So this effect can play a role for both. Yeah.
Can your theory in principle be tested in animals, or which of the aspects could one?
Another thing we do currently, or which Adam is doing currently, we want to really get this down for breast cancer. So we have a good collaboration at the Cross Cancer Institute in Edmonton, and they have breast cancer data and immune response data in the context of breast cancer. And so we would like to parameterize everything for this very specific example.
I think we had a very nice discussion, and it's clear that other questions will pop up. at a slower time scale after digesting the heavy message of your talk, Thomas. At least myself, I'm quite happy with the first talk in our seminar series, which provoked many comments and thinking, hopefully. I would like to thank you again, Thomas,
Yeah,
for
thank you too.
taking the effort of being the first speaker and giving such a nice presentation.
I'm glad it worked with all the technology.
Yeah, so do I.
But I'm sad I'm missing out on the beer garden next to the Elbe to have a beer afterwards.
Yes, that's you need your mouth and nose protection.
Oh, I see.
But I think you can open it while drinking. So thanks again, Thomas. And with that, I would like to share my screen. Do you see my screen?
Yes.
Okay. So next week, it's a pleasure to announce Klaus Pantel, and he will speak about circulating cancer cells. So it will be an interesting question for Klaus Pantel, circulating immune cells. So Klaus Pantel is from the university clinics in Hamburg, Germany, and he is a specialist in circulating cancer cells and how they can be used to diagnose certain states of cancer and maybe also predict fates of cancers. It's a pleasure to invite you all to this next talk. As this time we will send the access information one day prior to the seminar. Thanks to Thomas, thanks to all participants. And also we are very glad if you send us feedback, critical comments, suggestions for improvement under the known email address or by other media. Thanks a lot and see you next week. Bye-bye.
Thank you, Andreas. Thank you.